IMDb. How many of you are familiar with IMDb database? Heard of IMDb? Okay. So this is a very large movie database. I use it for a lot of projects in my courses. It has all the movie information, all the TV shows information for the entire world from 1925 onwards. So you can look up your favorite actor, actress. You can look up how many movies they have done, what kind of movies they have done, what kind of genre. So it's a very rich database that is very versatile, and we use it a lot because people can relate to it. People can understand some of the things because they are familiar with it. So what I ask them to do is to, take their favorite actors or actresses and find out how many movies they have made in their life career, and how many movies per year, and what kind of movies. So it gives them motivation to work on that. Similarly, how many of you have heard of the DBLP database? Movies, everyone is interested. DBLP, nobody is interested. So DBLP is a database of publications. So if you want to look up who has published how many papers in computer science, primarily it's for computer science, you just put DBLP and the person's name, and it will bring up all the publications of that particular professor. So you want to look up your professor's publication list, or somebody else their publications list, this is the place you want to go to. And it's a very useful database because both of these have a lot of structural relationship. And that is why they are good. Just like Facebook and LinkedIn, these are different sets of databases that have structural information. So graph model is appropriate for doing it. But the graph models we saw, simple and attributed, are not very good for that. So this is the plethora of databases. Are simple and attributed graphs sufficient for modeling and analysis of this data? The answer is they are very difficult. And we will try to establish that. So what is the challenge here? We want to analyze large multi-entity. So remember, we talked about entity. Those of you who know ER know what an entity is. It can be anything. Features or attributes of an entity, and relationships are the relationship between entities. So you may have multiple relationships among the same type of entities. For example, you have one relationship in Facebook, a different relationship in Twitter, a third relationship in LinkedIn for the same people. So you may want to ask, who are the most popular or socially active group of people across 2 platforms, or across 3 platforms, or across 3 social networks, all of them or one of them. Or you may ask, who are the most influential set of people in a subset. So how do you model this? Another example is airlines. You have multiple airlines. Their routes are not the same. Some of them overlap, some of them do not overlap. So we have used some American Airlines, and we have used some Indian Airlines for analysis. So you want to identify hubs, some of which we saw yesterday. Can we predict upcoming hubs? So we think that to model these kind of data sets with this characteristic, same type of entities, we think multi-layer networks, which we call homogeneous multi-layer networks, are useful. So what are homogeneous multi-layer networks? Okay. So that's one category. The second category is you have multiple relationships, but among different types of entities, not the same types of entities. It is different from Facebook and LinkedIn. What are the examples? IMDb is a very good example. We have movies as an entity, we have actors as an entity, we have directors as an entity, we have genres as attributes, ratings. So if you want to find out for the most popular actor groups from each movie rating class, which are the director groups with which they have maximum interaction. Now this is not a straightforward query. You cannot write a query for this one. So that's what you need to understand. That is why this comes to the analysis part, where you have to figure out how to generate this analysis based on the semantics and the relationship between them. So even though this particular data set is, we have loaded it in an Oracle database. So what I ask the students to do is to write some queries, not this kind of query, but a different kind of query, and also do the same thing using MapReduce to understand what is the difference between writing an SQL query, writing a MapReduce code, and the scalability issue. Highly rated actors working in similar genres who have never acted together. So these are not easy to answer. Similarly, there are other data sets like DBLP, where you have authors, you have publications, you have conferences, and authors collaborate. Authors publish in some publications and in some conferences. So frequently publishing cohesive co-author groups. How do you identify them? Most active periods for popular collaborators. So I'll show you some. These are the things I give as my class projects. So that will bring out, one of the students, she did a great job. I'm going to present her work in the next hour. So this can be modeled using what we call heterogeneous multilayer network, in contrast to the homogeneous multilayer networks I talked about. So that brings us to the question of what is a multilayer network we are talking about. So in addition to simple and attributed graphs we saw yesterday, we claim that multilayer networks, or MLNs for short, are needed for complex data modeling and analysis. First, let us understand what multilayer networks are and how they are different from the other two types of graphs. Are they also suited for analysis? So modeling is different from analysis. As I said yesterday, you can create a relational database, but if there is no querying or if there is no overlap on that, that database is useless. So modeling is different. Modeling allows you to understand the application data set clearly. Analysis is what allows you to derive inferences and knowledge from that data set. So these two are two different things. Whatever model we use should be good as a model, should also be good for analysis. So what is a multilayer network? It is a set of simple graphs termed layers or networks. That is where the name comes from. And the differences are that semantics of the layer can be determined by the modeler. So somebody is modeling the database, somebody understands the application area, somebody understands the domain. So again, domain knowledge is important. So you can say director directs an actor. So that's a relationship. Every actor who acts in a movie is directed by a director. Actors can have acted together in a movie. So in a movie you can see who are all the actors who have worked together, co-actors. Authors have collaborated on a paper. There are papers by a single author, there are papers by multiple authors. So that is collaboration. Choice of layer semantics based on objectives. Nodes between two layers can also be connected. Directs is a relationship between actor and director. Co-author relationship is between nodes of the same layer. So let us take this example and see how we can model this. So we cannot certainly model it a simple graph, right? But we can model it as a separate simple graph. So this one is modeled as 3 layers. One layer for Facebook. You can read it perhaps from this angle. Facebook friends, LinkedIn connection, and call network. So this is a multiple set of graphs. So you can say, what is the difference? The difference is that we are going to do the analysis on all the 3 graphs together, or some subset of the graphs together instead of a single graph. So this is a homogeneous multi-layer network. Homogeneous because the nodes are the same in all the 3. You see the same number of nodes are there, the same type of nodes are there. It is people. But the relationships are different. They are not the same. Somebody who is on LinkedIn may not be on Facebook. For example, I'm not on Facebook. I don't use Facebook. But I'm on LinkedIn just for the sake of presence. I don't use Twitter. It's too much of waste of time for me. So this is a multi-layer network. In addition, this is a homogeneous multi-layer network. Now, when we want to model other data sets which have multiple types, we cannot do it with this one because one layer will have one data set, another layer will have another type. So for that, we still use layers, but we also allow edges between layers. So one layer is actors, another layer is directors, third layer is movies. And this says this movie is directed by this director, this actor is directed by this director. So we can capture not only the information within the layer, we can also capture information across layers, relationships across layers. Now the question is, can we analyze this as a whole? Because you cannot just analyze this layer, then the connection to the other layer is lost. So this is what we call a heterogeneous. Heterogeneous meaning each layer has a different type of entity. Homogeneous means each layer has the same type of entity. Now once we have heterogeneous and homogeneous, you can also think of hybrid. Hybrid multi-layer networks where some layers are homogeneous, other layers are heterogeneous. There are links from some layers to another layer, but not to every layer. So there are 3 types of multi-layer networks: homogeneous, heterogeneous, and hybrid. So the question is, does this representation provide more clarity? Modeling clarity using MLNs, combination of the 2 choice of layers depending upon the set. So here the modeler has a lot of flexibility in determining how to define each layer. Also has the flexibility which layers should be connected depending upon the semantics, which layers are not connected. So this flexibility is very useful for modeling different types of data sets. Without that flexibility, it's very difficult to model, or the model will not be as good. So here, interactions among IMDb entities for the co-actor groups who are friends on Facebook, which are the directed groups with which they have maximum. So you can now ask questions combining Facebook data and IMDb data, which is not very easy to do otherwise. So because actors and directors are people, they also have a presence on Facebook, they also may have a presence on LinkedIn. So you can bring these 2 application areas and ask questions that cut across these 2 applications, which are extremely difficult to do otherwise. So here is an example of a hybrid MLN where This is a homogeneous layer. There are no connections from this, and these two are heterogeneous layers, but I should be able to analyze either these two layers, or these two layers, or these two layers, or all three layers. So that is the power of multi-layer network modeling and the capability. We'll come to the analysis part a little bit later. So this is a combination of HOMLN and HEMLN. Any questions, comments? I just hope that you are getting something out of this material. May be totally new, and it will take some time to sink. It's not easy to absorb all this in a very short period of time. So modeling clarity, layer is a simple graph, so we know that. It captures the semantics of a subset of features of the same entity type through intra-layer edges. So we differentiate between intra-layer edges, that is edges within a layer, and interlayer edges across two layers. For HOM element, interlayer edges are not shown because the entity sets are the same. So you assume that every node has an edge or has an implicit edge from one layer to another layer. What are the benefits of MLNs? Increased clarity and understanding. It is less convoluted because you can also do it using attributed graphs, but attributed graphs become very complex. You have different colored nodes, you have different colored relationships, and it becomes very difficult to understand. Existing single graph, this is very important. You can use existing single graph algorithms for analyzing multi-layer network. This is a big advantage or a big benefit because you don't have to develop all the algorithm from scratch, but you still have to develop some portions of it. Layers can be processed in parallel. This is a very huge advantage. So if I have 3 layers, and if I want to find communities in each layer, I can do it in parallel. So scalability kind of is built into this model. Partitioning of graphs and scalability is built into this model, which is not the case for the other models. Elegant handling of dataset updates. Why is this true? Because remember, all these datasets are changing. They're not static. Every year new movie information is added. Every year new publication information is added. People are joining Facebook and leaving Facebook every so often. Now, if updates need to be done, you have to do it only for one layer. Any changes to Facebook affects one layer, not other layers, which means whatever analysis I have done for the other two need not be repeated. This is a big advantage from the computation perspective, that you can reuse previously performed analysis and computations, and you don't have to redo them. So this is what I showed you yesterday. I think here I'm just going to add. So now we have 3 different types of graph models: single graph, attributed graph, multi-layer networks, and we are comparing it with modeling clarity, analysis availability, computational efficiency, drill down and visualization. We are claiming this is good for all of these, and some of the claim comes from one of the approaches we have developed called the decoupling approach for analysis, which is very, very, very efficient. We will try to show that a little bit in this one. So what is the current state? Compared to simple graphs, there are not many algorithms developed yet for multi-layer networks. So how can we analyze MLNs? That's a big question, right? If there are no algorithms, then what do you do? Typically, MLNs are collapsed. So what is done in the literature, in the community, is they take all the layers and then collapse it. It's very easy to collapse the layers. You can use Boolean OR, or you can use Boolean AND, depending upon what you want to do. But that results in loss of information. Structural relationship among entities are lost, cannot be maintained. When you merge two edges corresponding to two different relationships, now you cannot distinguish between them. When you merge two entities which are different, you cannot distinguish between an actor and a director. Drill down and visualization become difficult because of the loss of information. A few algorithms exist that are focused on the entire MLN and focus on interlayer edge traversals. This cannot be used for HOMLNs because there are no interlayer edges. Multiple traversal may be needed, making computation very inefficient. So our approach provides a much better way of doing that. So here is one slide on multi-layer network analysis alternative. So this is what I just now described. Perhaps the pictorial representation is easier to understand. Suppose say you have three layers, layer 1, 2, 3. These are homogeneous. Now I can combine or collapse all of them into a single aggregated layer. And then I can analyze this because I have an algorithm for analyzing simple graphs. But the problem is you lose information. The third alternative is to analyze the entire MLN as an MLN. Multi-layer network, you can use random walk-based analysis across MLNs. Final result, no partial result. And this is a complex algorithm. And you cannot say, do only 2 layers. Then you have to have a separate algorithm, do 3 layers. You have to have a separate algorithm. So what we have proposed is the middle one. And we call it the decoupling approach, network decoupling approach. This was done by one of my PhD students, and he's fortunately still continuing with our group and doing a lot of research. So what do we do here? How is this different from this and this? Here, we treat all the layers as independent layers. And we do the analysis of each layer separately. So each layer is analyzed separately. So think of, divide and conquer or partitioning approach where you do things on partitions and then combine the result into the whole. So this is what we call the analysis function. So you apply whatever analysis, it may be community detection, it may be centrality detection, it may be substructure, it may be motive. Apply this to each layer separately and then take the output, partial result from layer 1, partial result from layer 2, partial result, and then you compose them. You compose them to get the final result. And this composition is new. This is where we need to develop the composition function or the composition algorithm using the decoupling approach. But this stage remains the same, which is a huge advantage. So you analyze individual layers separately, and then you figure out how to combine so that the result you get here should be the same as the result you get here, or the result you get here. That's important, right? We want to get the same result, but in a slightly different manner, in a more efficient manner, and be able to apply parallel processing techniques for that. This is one of the reasons why we have been able to use MapReduce for multi-layer network analysis, because each layer can become a partition. If you want, you can further partition the graph in each layer if it is very big. I'll show that perhaps tomorrow. So combined lessons of layers 1, 2, and 3 using this. So we need to have 2 functions. One is the analysis function, which we already have algorithms for, but what we need to develop is the theta, which is the composition function. So what are the limitations of current alternatives? I have already explained that when you reduce it to a single graph, aggregate, combine, process the combined layer using existing algorithms. The problem is this will require exponential. If I have n layers, and if I want to do all the subsets of n layers, there are 2 to the power of n subsets. That means I have to generate 2 to the power n graphs and then analyze them, which is a very, very laborious or computationally expensive process. MLN as a graph process, the MLN as a full analysis, focuses on the layer edge, and here need to develop algorithms from scratch. See that previously available algorithms cannot be used because they're only for one layer, but you are looking at the entire MLN. Difficult to parallelize and scale. Repeated traversals MSN may be required. So there are a number of disadvantages for the current approaches. That's one of the reasons we try to figure out, is there a better way to do that? And one of the better ways to do that is the decoupling based approach. So what is decoupling based approach? I have already saw that. So it's a divide and conquer approach. Analysis functions specific partial results are composed systematically to fulfill the objective. So you generate partial result 1. As I said, you can even partition a layer and generate the partial result. Nothing stops you from doing it. We actually do that. If the layer itself is very large, say 1 million nodes and 5 million edges, then you can partition the layer and then generate it. That means you can do parallel processing for each layer. You can do parallel processing across layers. That's what adds much more punch into scalability. And then you compose. So this is a binary composition. So we compose 2 layers at a time and then take the results of the 2 layers and compose it further. You can apply it any number of times for any number of layers and you get the complete result. So this is what we call the decoupling approach, and this is a very powerful way. I'll show you some examples. So identify theta for various types of psi. Psi is known, theta is not known. So that is the challenge. Communities, we have done all of these. Communities for HOML and HML. Centralities, node, betweenness, closeness that I explained yesterday. We have done that for both HOML and HML. I have a PhD student working on weighted graphs now. So I am not even talking about weighted graphs here in this course, but that's another area where there is a lot of work and interest and need is there. Frequent substructures, I'll show you some demos tomorrow, motifs, and we have done a lot of work in graph creating. Establish their correctness, that's very important. So just like what we do in mining, any kind of analysis, establishing the correctness of your algorithm, your approach. Oops. Okay, I think I'm getting the hang of this. Oops. What happened? Power outage? Okay. Establish their correctness with respect to ground truth. So remember I mentioned ground truth, and in this case we use the first approach as the ground truth, collapse everything, find the answer, and that is what we consider as the ground truth. This is not moving. Okay, establish their properties. So we have all kinds of properties like commutativity, associativity, distributivity. These are also important to understand, not just the algorithms, and develop efficient algorithms. And there is flexibility of analysis compared to traditional approach. The advantage is existing algorithms for a monoplex can be used directly. Combinations are easy to analyze. I can take just 2 layers because of the decomposition. I can just analyze 2 layers and split it. If I want 3, I already have the layer analysis for 2 layers, add the third analysis and then compose it. The negatives are no need to generate, store, analyze each attribute feature combination. We don't have to generate and store as in the first case. If you have n attributes, you have exponential combinations. We don't have to do that. Instead, MLNs generate, keep, and compute only n layers. So we have reduced a exponential problem to a linear problem. That's a very huge advantage. Exponential is computationally very difficult, linear is very easy. Composition allows this approach to compute selective subset of attributes, linearizes exponential complexity. Benefits, we retain the MLN modeling clarity it brings and semantic. That means we don't merge anything, we don't coalesce anything, we don't put two different entities as one entity. We keep them separate. So structure and layer semantics are preserved. Leverage single graph algorithms. As I said yesterday, we use InfoMap, we use Louvain for community, we use Subdue for substructure detection, we use different centrality algorithms for that. Structure preservation, no loss of information, no distortion. Efficiency, exponential combination of graph reduced to linear combinations. Flexibility, I can choose any number of subsets, number of layers to analyze. I want to analyze Facebook and LinkedIn, Facebook and Twitter, or LinkedIn and Twitter, which is difficult to do in the other approach. Amenable to optimizations. I'll show where we can optimize Boolean expressions by using the theorems that we already have. Parallelization opportunities, ease of dataset updates that I already mentioned. Most importantly, this approach is application independent. It doesn't matter what application area you are analyzing, you don't have to worry about it. You just have to worry about the semantics of the layers while creating the semantics, and then you have to translate the objectives into corresponding computations on the layers. But the composition algorithm doesn't change. It is developed once and used. Same as single layer algorithm, communities are the same, whether it comes from a chemical domain or a biological domain or from Twitter domain. A community is a community. So, I don't know, I think she's going to come and stop me soon, but I still have a lot of steps to go. So, some results. So, we use Boolean and our composition. We have done it for HOMLN and HMLN. So, if I cannot show all of them, I'll show some partial. So, this is for community detection. We have done it on various kinds of data sets from different domains. Real world data set, DBLP and IMDb are real world data sets, and UK accident is a real world data set. We use RMAT. Remember I talked about synthetic data sets and why we generate synthetic data sets. So we have used RMAT and generated. So this gives you some idea of number of vertices, number of edges in layer 1, number of edges in layer 2, and number of edges in layer 3. So we have used 3 layers. I will show you a Facebook example where we have generated 11 layers. Look at this. This IMDb dataset has 13 million edges. That's a reasonably large dataset. Others have 235,000, 230,000, and so on. This one. So, what is AND composition? What is AND composition? Single graph approach for communities, we call it C single graph AND. Combine the required layers using AND operator. So for example, let's say this is a layer and this is another layer. These are HOMLN. And I am going to combine these two using AND, meaning so remember the nodes are same. If there is an edge in this layer and an edge in this layer, then there will be an edge in the AND layer. For example, 1, 5, 1, 5 comes out as a layer. There are some edges are not there. So something is missing. Okay. So these are the two layers, and this is the AND graph. So if I AND these two graphs, I get this graph. I get this graph. That is the AND, Boolean AND of layer 1 and layer 2. Now I will find communities in that layer, and that is what I need to get for these two layers using the decomposition approach. So this is the ground truth. And the communities here are what is shown in highlighted area. There are multiple communities. So for example, this is a community, this is a community, this is a community, so on. And so specification is, what I want to do is to first take a single graph approach to SGN. Now G1 and G2 and GT and layers. Now GA is the original MLN layer or not layer. Communities are used as the ground truth. Most socially active groups of people across these two platforms. So this is what I want to do. I want to get this from applying my decomposition algorithm on these two layers using the composition function. So correctness is based upon the this one approaches for two layers. So we developed two different algorithms which we call CV AND and CE AND. So this is AND aggregation. CV is a community detection based upon vertices or node based intersection. CE AND is an edge based intersection for computing the community. What we'll see that this algorithm is not as accurate as the edge-based algorithm, and edge-based algorithm takes little more time than the vertex-based algorithm. So again, always in computer science we have time versus complexity trade-off, accuracy versus time, accuracy versus memory, and so on. So here are the approaches. So I take communities of layer 1. These are the communities that come out of layer 1. These are the communities that come out of layer 2. And in the CE and algorithm, I am going to intersect the edges of these communities, this with all of them, this with all of them, and then I generate the result. Now that result should be the same as the ground truth. So I think you guys are using some earlier slides. There is some information missing here. Okay. Okay. So I hope you understand it. So the decoupling approach says that this is the psi. Find communities for this graph. Find communities for this graph. The composition is the intersection of these communities from each layer, and then get the result. So this should be the result. Now you can go and check whether this result is close to this result. That's what we want. So how do we analyze the cost? Cost of doing decoupling approach versus cost of doing the ground truth approach. Total decoupling approach cost is one-time cost of layer analysis plus the cost of combining partial results. One-time cost is one community, set of layer-wise communities generated once using existing algorithm, and if you do it in parallel, time is bound by the largest graph or the densest graph which has the highest number of edges. That determines the total time. Cost of combining the results. CV AND algorithm of composition uses one scan of community nodes per required layer, C and 1 scan of community edges per required layer. So remember, always the number of nodes is less than the number of edges, typically. So CE and does little more, take a little more time in its computation, but gives better results. So the total cost is the max partial result combination cost, which is less than the minimum one community cost. This is what we'll show. Cost of ground truth, cost of generate end layers plus cost of retaining communities, and cost of CV and we have shown is less than the cost of CSGN, and cost of CN is less than the cost of. So both costs are way less than the ground truth, cost benefit amortized over large graph analysis. So again, developing an algorithm is one thing. Testing it, you cannot just test it on one data set and say it gives you good results. Maybe it's an outlier. Maybe you just lucked out. You have to test it consistently on several different data sets to make sure the result is consistent across data sets, across characteristics. So as I said, we have experimental results for, I'm going to show you 5,000 accidents from UK from 2014. So layers, 2 nodes are connected if accidents occur within 10 miles of each other and had similar light or weather or road surface condition. Now this 10 miles is what we have chosen. You can do it for 5 miles, you can use it for 1 mile. It's a similarity condition. 4 and composition analysis. So we have generated different, 1 layer for light, 1 layer for weather, 1 layer for road, and we can analyze these two, these two, these two, these two, and all of them, light, weather, and so 3 layers, 3 pairwise analysis, 1 all 3 analysis. Community detection algorithm used is InfoMap, accuracy metrics, normalized mutual information NMI, or you can also use modified NMI, which is slightly better because it takes network topology into account, whereas the first one doesn't take the network topology into account. Oops. Okay, here comes the result, proof of the pudding. So, accuracy. So this is accuracy with respect to the ground truth. If it is the same as ground truth, it is 1, otherwise it is less than 1. So you can see that for CV and the accuracy is less than for CE and. Both NMI and MNMI show similar values. So this shows that one composition algorithm is better than the other algorithm in terms of accuracy. When you look at the efficiency, this is the ground truth cost. This is the cost incurred by CV and. This is the cost incurred by CE and. So you can see that the cost of CV and is much better than the cost of CV and. So there is 71% improvement to the ground truth, whereas this only has 20%, but this gives close to 1 accuracy, this gives less than 1 accuracy. So this is the trade-off that you have to understand and deal with. So trade-off is higher the accuracy, lower is the efficiency. CVN and CN clicks in general CN for accuracy and efficiency. So also, I should point out, we talk about visualization, drill down. It's important to show it in a way that is easy to understand. Just don't dump numbers so that, and then let the viewer figure out what it is and confuse the user so that you can hide behind the numbers. So don't do that. Here is component cost analysis of decoupling approach of CVN and CN. So here we have taken the lowest analysis cost and the highest composition cost. Just to contrast, the lowest analysis cost and the highest counted, and you can see there's a difference of 99% for CVN and a difference of 50% for CEN. So even CEN, which gives good accuracy, is 100 times better than or half of the other one. So worst case analysis, maximum cost of combining the partial result is significantly less than the minimum cost of detect one layer communities. This is the two extremes. We have taken the maximum of what we do and the minimum of what we do on the others, and look at this one. If you take the maximum of this and minimum of that, it will be even more. Trade-off between efficiency and accuracy. So here, these were for the UK accident dataset. These are for the IMDb database. You can see similar results. In this case, CVN performs much worse than CEN. Here it is 0.4, this one is close to 1. Same with this one. Here it is 89% and here is 80%. So this one is very good, even though a little bit more than CVN, it's not very much more, but the accuracy is way higher. This is the accident data set that I showed you and the efficiency. So trade-off higher accuracy, same thing. This is DBLP data set. See the difference, how it varies. The accuracy here is quite high for CVN and even better for CEN. These percentages vary. And this is for RMAT, synthetic data. Again, you can see that CVN gives better. Now why is this? Why is that different data sets give different types of accuracy, different values of accuracy? It's not the same, but the trend is the same. CVN always gives lower accuracy, CEN always gives higher accuracy, response time trend is the same. So this is what is very important to understand. This depends upon the graph characteristics. One graph may be very dense, one graph may have too many edges, one graph may not have it, connectivity is different. So all of these things come into picture to understand what is happening. So that is why it is not enough to do one experiment and say, I'm done, everything is fine, I can go home. Give me my PhD, I'll go home. Okay? So component cost analysis again for different data sets, and you can see that it's very similar. And so you can do complex composition. So I just showed you L1 and L2, but we can do L1 and not L2 and L3 or L4. We can do any Boolean expression. Right? Now we have 4 layers, L1, L2, L3, L4. The approach is the same, composition is the same. So you do community detection for L1, L2 is the complement of L2. Take the complement graph instead of the original graph. So you can always create the complement graph, means fill the edges that are missing from the other graph. And then do the same composition in exactly the same way. So this is not just limited to one particular pair-wise combination. You can apply any Boolean expression you want. In the next lecture, I'll show you some good examples of this. We can also do R composition. The composition algorithm is different. Analysis algorithm is still the same. So I'm not going to give you the algorithm. I'm going to just show you some results for IMDb. Now, similar results are obtained for accuracy and efficiency. Similar results are obtained for RMAT, for accident database, and component cost comparison. So for R, the algorithm is more complicated. So again, the challenge is in developing these composition algorithms so that you get the highest accuracy possible. The goal is to obtain accuracy of 1. Efficiency improves with more analysis. Decoupling approach is amenable to optimization. So for example, if you are given an expression such as this, so this is a Boolean expression, right? We have and, not, and or. We can convert using De Morgan's law. I hope you guys remember what De Morgan's law is. In circuit theory, that's very important, and distribution laws. And then you can convert it into a different expression which is easier to process, which is easier to analyze. So if you analyze this expression as is, it will take more time, less efficient than if you analyze this expression. So optimization of expressions can be done because we already have laws, De Morgan's laws, to convert into conjunctive normal form or into distinctive normal form. So this shows why this optimization is better, and then here are some results for that. Perform cost analysis of all possible specification alternatives for Boolean comparison. Reduce number of comparisons. Start with AND. The reason you start with AND is the AND graph is smaller than the OR graph because the number of edges in the AND graph is less than the number of edges in the OR graph. Reduce not composition. So depending upon the initial graph, that's what I said. If you know the graph correctly, if the initial graph is very dense, complement is very sparse. So it's worthwhile doing the complement first. If the original graph is not very dense, then you want to do it at a later stage. So here we are just showing that we have done for different data sets. This is the Facebook. I'm not going to show it today now. I'm going to show it in the next one. So in the Facebook, we have 11 layers. Age layer, gender, relationship, political views, locale. There are 5 social traits called the Big 5. Conscientiousness, I don't fully remember, I'll show you what they are, and we can analyze all of them. You can see that this is actual Facebook data from Sweden, and they had the data set, so we collaborated with them. You can see that even the number of nodes is very small, number of ledgers are very large, in millions. Potential actor collaborations. Surprisingly, our ma'am has not come to ask me to stop, so I'll continue. So this is interesting because this is something you can relate to. Which highly rated actors work in similar genres? So genre is comedy or horror or sci-fi. Here she comes. I was wondering. But have not co-acted together in any movie. And you can express this analysis using a Boolean expression, not co-acting and genre and average rating. And if you do that, these are the results we got. These are actual names of the actors. If you know them, you can relate to that. You can relate to that and see, and these are the genres. These people typically act in action crime. These people act in drama. Tom Hanks, perhaps you know, Russell Crowe, you know, Kate Winslet, who did the Titanic, you know, Johnny Depp, maybe Tom Cruise for sure, DiCaprio. So you can see the names and who satisfy this objective. So this is the power of analysis or inferring meaningful knowledge from the data set. If you want to figure this out, I mean, IMDb data set is very large. the relational version has, some of the relations has 50 million rows. So reports in 2017 talks of casting Johnny Depp and Tom Cruise in pivotal roles in universal title Dark Universe. I don't think that happened, but so that confirms that these people did not work together. So somebody is considering, hey, these are very popular actors. If I put them together, perhaps my box office revenue will be higher. Similarly, widely accepted collaborators, which collaboration groups has published in both highly ranked conferences but have never published in either Medium or this one. Again, these are names of people. Some of them you may recognize. For example, Surjit Chowdhury works for Microsoft. Who else you may know? He works for Arizona State, he works for Santa Barbara. So some of these are known names. So he won the VLDB 10-year Best Paper Award. This is from internet. This is to validate our results, whether we are getting the correct results. How do you validate it from an independent source? So he got it, and Vivek Best Paper Award, where Nicholas Bruno, apart from winning ACM Sigma Contributions Award. So this guy has 24,000 citations in Google Scholar and so on. So we do the analysis and then we check whether this analysis is correct. Today it's a little bit easier to do it because of Google and all the information that is available in Google Scholar and H-index, I-index, all those things come into picture. Okay, I think, do you want me to stop here? Where is she?
Just 1 minute, I'll call her.
Huh? Stop, continue?
Sir, they are confirmed.
Huh?
They are confirming.
Stop?
No, sir, they are confirming.
Continue. Okay, I'll be happy, but your tea is delayed. Okay, so homogeneous MLNs are easy to analyze to some extent. We had to develop algorithm for heterogeneous layers, which are much more complicated than homogeneous. Actually, you may be surprised, a lot of this work was.
If you want, you can take a break.
Break?
Yes, sir.
I knew that. I knew it was coming. Okay.
So breakfast will get served in
ठीक है. Okay, good morning still. Let's continue with this one. So we saw some experimental results for homogeneous multilayer network. This one is about heterogeneous, and heterogeneous is a little more complicated because of the interlayer edges between two layers. Okay, so limitations, as we have seen, no structure preserving definition, type independent, projection based. So typically you aggregate these two layers into a single layer and then you compute the communities for that aggregated single graph. So this is what we use as the ground truth, but there is a lot of information. As you can see, the colored nodes have become black. There is no difference between these nodes and these nodes. There is no difference between the relationship within a layer and the relationships across layers. So again, we have used IMDb database with different sizes, directors, actors, movies for doing that. We have also used DBLP HTML. So we can actually create either homogeneous MLNs or heterogeneous MLNs depending upon what semantics we want to capture from these data sets. So it is not that given a data set, it can be modeled in only one way. That's important to understand. The same data set can be modeled in so many different ways, and each of them will give different semantics and different structure. So some of the analysis that we wanted to perform are these things. I will not go through all of them. And conference-wise, which are most cohesive groups of authors who publish frequently, including types. Now, remember I introduced the notion of bipartite graphs. For heterogeneous composition, we need to use the bipartite graphs. And when you use the bipartite graphs, we are doing different types of matching, maximum weight matching with ties, maximum weight, redundant matching, maximum weight matching. So these are the data that we are going to compute, and there are other things that you can do. So I'll show you just some efficiency results. Again, the efficiency results are very similar. So this is for the execution time in seconds for the actor layer, director layer, and movie layer, because the movie layer with the rating is quite dense, and because it is dense, it takes more time for computing the analysis. And base case, movie, actor, director, movie. So these are the different timings that are there. So the cost of all iterations together is more than an order of magnitude less than the largest one-time cost. So this is being borne out again and again in all of our experiments. So we feel pretty good about the decoupling approach and the composition, because the composition time is very small compared to the analysis time. So this is another objective about potential actor-director collaborations. For the most popular actor groups from each movie rating class, find the director groups with maximum interaction who also make movies with similar ratings, including tests. So some of these objects purposely we have chosen complicated ones so that we can exercise all the complexity that we can use. So for example, this uses movie layer, actor layer, director layer, and movie layer again to finish the cycle. And this is our visualization. As I keep saying, this is generated more or less manually. We get data because there is no tool to generate this kind of things. What this shows is these are the communities within a layer. This is a movie community, these are actor communities, and these are director communities. These links indicate the most popular actor groups. So these are the most popular actor groups and their relationship to movie communities and their relationship to director communities. If there is a blue edge from here to here to here to here, that means those three groups satisfy this particular objective analysis. So that's how you do that. And this can also be represented using the word cloud. So this is one representation, this is another representation where we can put the actual name of the actors for certain communities, not all the names, and then show. So this is one of the groups, and if you are familiar with actors and directors, you can confirm through independent sources that this is correct. Similarly, we have others. So I'm going to wrap this up. Potential actor-director collaborations. So DiCaprio, Mendes, and Swank. So this brings us to the end of this module. We will start with module 10.